All right, let's walk through some general terminology that we're going to need for the rest of the semester. So this is the start of chapter 3 in your textbook if you like to follow along. So these terms are terms we're going to use throughout the semester to make sure that we're really consistent. So make sure you have these jotted down and that you understand what each of these mean. So the first thing we're going to define is a process. It's any operation or series of operations by which an objective is accomplished. So it's a series of steps, it can be a series of reactors, it can be a series of modules, but the process encompasses the entire system. Next, we have what's called an input feed, and for our purposes in this class, inputs are things that go into reactors or go into the process itself. So the process is going to be represented by a box when we draw our diagrams, and the input is going to be drawn as an arrow that goes into the process. We can also have what's called an output, and sometimes this is called a product. And this is what leaves the process. So it's going to be an arrow coming out of a box or out of a circle. And product is an important term because when you start to read your problems and your problem statements, you will see the word product or input or process, and you need to know which part of the flow diagram that is as we start to label those. A process unit is an individual process within a multi-step process, so it's the individual box that represents the reactor as we start to draw our diagrams, and we'll talk about how to draw flow diagrams in class. That's something that we need to talk about in person. But the process unit is actually just the box itself. The entire process is all of those inputs, outputs, and multiple processes. Design is the formulation of a process flow, so taking a bunch of individual unit processes and their associated variables and putting them together all into one big thing. So that's design, right? That's what we do as engineers. So we've got to understand the individual processes first before we can design something more complicated. We also have the word operation, so this is going to be day-to-day performance of an existing process. So once we've designed it, it then has to operate for a long time. So how it's going to operate on a day-to-day basis is very important. This is going to be important when we talk about steady state systems. And then the next two terms are a little bit more specific to certain industries, but you might hear the word debottlenecking, and basically what that is it's troubleshooting. It's a way of identifying or modifying steps in a process so that you get better efficiencies or better throughputs normally at the end of the day. And then you may also hear the term turn down, and that's adjusting the process to decrease product demand over time. So that's some general terminology. Some other things that we want to talk about very quickly are mass and volume. You've likely seen these in chemistry before, but we are going to deal extensively with mass and volume in this semester. So I want to remind you that density is equal to mass divided by volume, and that is represented by the symbol rho. That's a Greek letter, so it looks like a little P that's basically slanted. So that's density. The next one is specific volume. So specific volume is 1 over the density because specific volume is defined as a volume per unit mass. So V over M is the reciprocal of density, which is why specific volume is 1 over the density. Another important thing to remember is that densities of pure solids and liquids are essentially independent of pressure, and they vary slightly with temperature. So for the purpose of this class, we're looking at things that are independent of pressure and only are going to vary slightly with temperature. Now, that's not always true in the real world, right? There's lots of different cases, but for what we're looking at in class, this is one of the assumptions. That's where we're going to be making to make a little bit more idealized systems to solve for. And then the last thing to talk about is specific gravity. Specific gravity is density divided by a reference density. And generally when it comes to the reference density, the reference density is the density of water for this class. The density of water, this is a good number to write down, is 1,000 kilograms per meter cubed or 1,000 gram per centimeter cubed. So that's a really good number to have written down in your note, 1,000 kilograms per meter cubed or 1,000 grams per centimeter cubed. So that's important. All right, so let's test your understanding really quickly. We want to know, well, what are the units of specific gravity? Well, specific gravity is a density divided by a density. So in that case, let's say that density has units of kilograms per meter cubed. If we divide kilograms per meter cubed by kilograms per meter cubed, we get 1. So specific gravity itself is unitless. Take a pause in the video and try to do the number 2 question. If we have a substance A and substance B that each have a density of 1.34 grams per centimeter cubed, if we have 3 centimeters cubed of A and 3 centimeters cubed of B, will they have the same mass? Take a pause in the video, see if you understand this concept. All right, let's take a look at the answer. So if you rearrange the density equation to solve for mass, mass is equal to density times volume. So if the density is the same and the volume is the same, that means the mass must be the same. All right, so that's just a quick review of mass volume concepts. We're going to use this throughout the semester, so make sure that these are crystal clear before you go forward with the next video.